Welcome back. In this section we will discuss redox flow batteries. Most people will be unfamiliar with redox flow batteries. However, they may be one of the most attractive options for large-scale stationary storage, the storage of electricity in buildings, for example. As you can see in this figure, redox flow batteries are generally a little more energy dense compared to lead-acid batteries, while still having a similar power density. When we envision large-scale storage of electricity, we do not really care for high performance and size. For example, if a battery is 2 times as big but 10 times lower in price, most people will opt for the cheap, big option when it comes to stationary storage. Also, safety concerns like flammability becomes more important. So, what is now a redox flow battery? In essence, it is a battery where the electricity is stored in liquid solutions that sit in tanks, the catholyte and the anolyte. Whereas in a normal battery, the energy is stored in the solid cathode and the anode. The solutions are pumped towards a cell that has current collectors. There we will have 2 redox reactions that will produce electricity. A great feature of a redox flow battery is that it decouples power output from energy storage. When we need more power, we can add extra cells. And when we need more energy storage, you can add an extra tank. For normal batteries, this is not so easy. You cannot just make bigger electrodes, for example. In this photo, you can see the Turner Energy Storage Project battery in Pullman in Washington. It can deliver 1 megawatt of power and provide 4 megawatt hours of energy. A commercial example is the vanadium redox flow battery. This type of battery was developed by Maria Skylas-Kazakos in the 1980s. When considering a discharge, on one side vanadium 2+ becomes vanadium 3+, and on the other side a vanadium dioxide cation will become a vanadium oxide cation, which is actually vanadium 5+ going to vanadium 4+ if you think about it without the oxide. All this is happening in sulfuric acid. When we do the calculations, the standard cell potential, when all standard conditions apply, we get 1.26 volt for this battery. Although sulfuric acid may sound a little dangerous, the vanadium redox flow battery is very safe, considering that the electrolytes are non-flammable. And although you see that the solutions are beautifully colored, vanadium is a toxic metal for the environment and for humans. But when handled correctly, this is a minor risk. Also, vanadium is an expensive metal that is classified as a critical raw material by the European Union. Therefore, although simple in design, vanadium redox flow batteries are still quite expensive. Therefore, there is a big effort to find other chemistries for redox flow batteries. In the literature, there are many examples, and although you can make them with flammable toxic organic solvents, a lot of emphasis is placed on aqueous electrolytes. This is keeping cost and safety concerns at bay. In this table you can see some of the most investigated redox flow batteries. In a flow battery, the solutions are pumped from tanks to cells. It should be noted that the pump will also use some energy. It is therefore apparent that this energy use is not in the same ballpark as the battery can deliver. Some setups in literature will use viscous suspensions, which will be much more energy intense to pump around. This is called a semi-solid redox flow battery. It will use particles in suspension, and the electrons travel from the electrode to the particles through a carbon black suspension. It has the promise of much higher energy density, but comes with many caveats, like the pump efficiency and lifetime, for example. Also, internal resistance is more important in flow batteries. Ions need more time to get to the electrode. This will create different resistance layers that can influence the power output of a cell. In the bulk electrolyte, ohmic resistance will be dominant, while closer to the electrode, diffusion will be important. On the electrode itself, absorption will play the most significant role. Last but not least, the 2 sides of the battery will need to be in contact with each other, just like in a normal battery. When an electron, a negative charge, travels from one side to the other, there will need to be charge compensation in the solution. This could mean that a positive ion travels along the same direction or a negative ion travels in the reverse direction. However, if the catholyte and the analyte are with each other in contact, they will mix and thereby ruin the battery. Therefore, the solutions are separated in the cell by the use of an ion selective membrane. There are special membranes that will only allow certain ions to go through. This is mostly based on charge and size. In the case of the vanadium redox flow battery, Nafion is used. Nafion is a sulfonated fluoropolymer, and it is a proton selective membrane. It will only allow protons to go through. So when we discharge the vanadium redox flow battery, electrons will go from the analyte to the catholyte through the external circuit, and at the same time protons will go from the analyte to the catholyte through the Nafion membrane.